Welcome to section 10.8, Vector Equations of Lines in Space. After this section, we should be able to answer these questions. What is the general vector equation of a line in space? How do each of the components correspond to the equation for a line in 2 dimensions? Where do each of the terms in the general vector equation come from? Well, to develop the equation for a line in space, we need to look at its analog in 2-dimensional space. So first, let's ask ourselves the question, how do we describe a line in a 2-dimensional space? Yes, y equals mx plus b, where m is the slope and b is the y-intercept for the line. So what information do we need to make our description unique to a particular line? Well, we need to know these two values, the slope and a point on the line. So how could we describe a line in 3-dimensional space? Well, we need those same pieces or types of information, a point on the line and the direction our line will take away from that point. So if I'm starting at B, I move a rise over run, or a slope, of x units. So here is our equation for a line in space. R is equal to the position vector P plus D times a unit vector. And we're going to see how very closely this vector equation lines up with our equation for a 2-dimensional line, y equals mx plus b. Here we've got r being the equation for our vector, or our line in space. And it's the position vector to any point, a variable point on the line. So it's equivalent to y, where y is some point on the line described by this expression. P sub 0 is our position vector to a fixed point on the line. Just like our b value is a fixed point, our y-intercept, on a 2-dimensional line. Now d is a parameter, or a variable, equal to the directed distance from our fixed point p0. p0 we're going to call x0, y0, z0, to some variable point on the line. So that's this x value. How far away from our fixed value are we moving to find our new value? So that's our x. Now the unit vector is basically the slope. It's giving us the direction in which we're going to move. All right? Where our unit vector, or u, is c1i plus c2j plus c3k, right? And as we remember, our unit vector is exactly equal to 1 unit in length. So if we expand our notation to express what p and u are, then our vector equation for a line in space looks like this. R is equal to x sub 0 plus c1, our direction cosine in the I direction, times d, I, plus y0 plus c2d times j, plus z0 plus c3d k. So x0, y0, and z0 are our starting value. That combination of information is just like our b, or y-intercept, in a 2-dimensional space. And then c1, c2, and c3 are our slopes in the x, y, and z direction, I, j, and k. And then d is our common variable. So really, our vector equation is made up of 3 separate linear equations. Our x value, or our b value, plus our slope times our variable. Our b value plus our slope times our variable. And our b value plus our slope times our variable. Now let's look at an example. We want to find the particular equation of the line that contains the fixed point 5, 11, 13, and that is parallel to the unit vector 3/7 I plus 6/7 j plus 2/7 k. Well, let's remind ourselves of what the equation for a line looks like. Now remember, it's simply three separate linear equations where our variable is d instead of x. So this actually becomes a fairly straightforward problem. Our line in space needs to be the fixed coordinate for x plus our c1 or I component of the unit vector 3/7 d instead of x in the I direction. Can you figure out what the j component's going to look like? Yes, 11 plus 6/7 d j plus, and then our third component, which would be 13 plus 2/7 d k. So let's double check. And there it is. Let's look at another example. Find the point on the line in example 1 that is a directed distance of negative 21 units from P0. So what they're asking us to do is, here's our equation from line 1. We want to move along that line negative 21 units. So that just tells me to replace my d value in each of these components with negative 21, because together they move 1 unit in the appropriate direction, and I want to move negative 21 units. So I take 5 plus 3/7 times negative 21 to find my I component, plus 11 plus 6/7 times negative 21 to find my j component, and finally plus 13 plus 2/7 times negative 21 to find my k component. Now 3/7 times negative 21 gives me negative 9 plus 5, so negative 4i plus 11, so that's again negative 18 plus 11, so negative 7j, and finally 2/7 times negative 21, 3, negative 6 plus 13 is 7k. So that would be my position vector to a place on the line, and the point itself would be those component coefficients, so negative 4, negative 7, 7. There we are. Notice how my answer was a coordinate because I asked for a point, not the position vector to the point. All right, here's another question. Find the point where the line in example 1 intersects with the xy plane. So if I were going to think about what we're talking about here, let's draw my x. My xy plane is the area here. Let me see if I can highlight. So it's in this area down here. And what that means is I have a line that's coming down somewhere going through this plane. Maybe right here. And I want to find where that point is. Well, when I look at this picture, this line I drew arbitrarily. So that means that the x and y coordinates could be anything. Don't know what x is, and I don't know what y is. But I do know that since it's intersecting the xy plane, z has to be equal to 0. I'm not moving anywhere up and down the z-axis. So I'm going to take that information and I'm going to use it in my equation. If z equals to 0, then this component right here has to be equal to 0 for that point. So that tells me that 13 plus 2/7 d has to be equal to 0. So 2/7 d equals negative 13, and d equals 13 times 7/2, which is equal to 91/2. Now that I have that information, which is also 45.5, I can use that value for d in these other two linear components. If d equals 45.5, then my x-coordinate is going to be 5 plus 3/7 times that 45.5. And my y-coordinate is going to be 11 plus 6/7 times 45.5. So that tells me that my coordinates are going to be negative 14.5 and negative 28 and 0 for z. Alright, here we have a line containing the point 5, 3, 1, negative 1, and it has direction cosines 6/11, negative 2/11, and 9/11. First thing we're being asked to do is write the particular equation of the line. Alright, well, remember that this point 5, 3, negative 1 is going to be the x0, y0, and z0 in my equation for my line. My direction cosines are also the coefficients of my unit vector, which also fit right into the equation for my line. So the equation for the line here is just going to be my x point coordinate plus my c1 times d, 6/11 d, I, plus my y coordinate, 3, plus my c2 coordinate times d, j, and my z coordinate, negative 1, plus my c3, 9/11 d, k. So there's my equation for the line. Now, to find the point where the line intersects the plane 7x plus 4y minus 2z equals 39, I have to think about the fact that this point on the line, this r expresses any point on the line, and here I have my equation for the plane, so I need to know when they are the same. So to find a specific point on the line, I would need a value for d, which would give me an x-coordinate. And then that same value for d would give me a y-coordinate. And the same value for d would give me a z-coordinate. So if this is my x-coordinate, and this is my y-coordinate, and this is my z-coordinate, I can use substitution to replace the x, y, and z in the equation for the plane with those expressions. So I would have 7 times 5 plus 6/11 d plus 4 times the y information, or 3 minus 2/11 d, minus 2 times the z information, which is negative 1 plus 9/11 d. And that's going to have to be equal to 39. So we can run some algebra here. 35 plus 42/11 d plus 12 minus 8/11 d plus 2 minus 18/11 d equals 39. If I add my constants, I've got 35 plus 12 is 47, plus 2 is 49. So 49 equals, or plus, let's see, 42 minus 8 will be 34, minus 18 will be 16. So 16/11 d equals 39. So 39 minus 49 is minus 10. So 16/11 d equals minus 10. And d would equal minus 10 times 11/16, which would be negative 110 sixteenths, or negative 55 eighths. I now have a value for d, but my question is to find the point where the line intersects the plane. So I'm going to use that value for d in my equation for the line. So 5 plus 6/11 times negative 55 eighths. My value for d will give me my x coordinate. My y coordinate will be 3 minus 2/11 times negative 55 eighths. And my z coordinate will be negative 1 plus 9/11 times negative 55 eighths. And if we do the math, we'll see that our point is 1.25, 4.25, negative 6.625. So let's recap. What is the general vector equation of a line in space? Well, here it is right here. R, our line in space, is equal to the position vector P plus D times a unit vector in the appropriate direction. How do each of the components correspond to the equation for a line in 2 dimensions? Well, R is our y value. P0 is our fixed point on the line, so it corresponds to the b in our y equals mx plus b equation. D is the directed distance, so that's the same as our x variable. D is our variable in the vector equation. X is our variable in the linear equation. And finally, u is the unit vector in the direction of the line. So just like our slope tells us how to move away from our original point, u tells us how to move away from our original point on the three-dimensional line. So it's our m value. Where do each of the terms in general vector equation come from? Well, that's a similar question. Our u is a unit vector, so it's going to take the form of c1i plus c2j plus c3k. And p0 is a position vector, so it's going to take the form of x0i, y0j, and z0k.